Hello, we are Team 19093, and our senior design project is a multi-channel head cap for transcranial acoustoelectric brain imaging. Our project is sponsored by Electrosonics, and our team members are listed below. This slide is a representation of what our poster would have been on design day, and provides a general overview of the entirety of our brain imaging system. Around 100 million Americans have been diagnosed with a neurological disease over recent years. Our system aims to combine high-resolution imaging with efficient signal processing to scan the brain in a research setting. We have a 32 electrode system that will integrate with hardware provided by our sponsor. The TABI system will minimize the noise during the scan process, and the acquisition data will then be processed and displayed in a close to real-time fashion. Additionally, our team used a phantom head model to simulate electrical function in the brain. The head cap is made of flexible TPE copolymer filament to expand to a variety of head sizes and utilizes electrode housing clips to maximize the electrode's contact with the phantom head model. There are active circuits used in conjunction with passive gold cup electrodes that have made our system capable of sensing from 1 Hz to 4 MHz in addition to sub-microvolt signals. Finally, the TABI system performs digital filtering and decimation to graphically display the obtained data.
Moving on to our system block diagram, which starts in the top section with a head cap subsystem. The head cap itself houses the array of electrodes as well as the active circuit boards. Its primary purpose is to collect the signal data and send it off to our sponsor's signal conditioning and acquisition device. From there, the device will condition and digitize the signal and then pass it off back to our signal processing subsystem displayed in the lower half section. This subsystem will perform sample decimation, digital filtering, as well as store the data and display it in close to real time. Our system description reiterates and adds detail about what was shown in the system block diagram. The two subsystems together make up the acoustoelectric imaging system. The head cap subsystem is the hardware used to sense the signals from the brain. It's also responsible for delivering that signal to the sponsor's signal conditioning and acquisition device. The signal processing subsystem is a software package, which is responsible for receiving the digitized signal back from the sponsor's device. It also decimates the data to improve efficiency, performs digital filtering and processing, stores the data, and finally provides a graphical display set to the user's specifications. There were a number of key concepts our team had to consider while designing our system to satisfy the design requirements. The first was noise minimization, where we focused on isolating our signal input from the output. To accomplish this, we utilized a differential amplifier as well as coaxial cables to shield from external noise. We also designed our PCB around this focus. This included minimizing the length of the traces as much as possible and isolating the signal traces from one another. The second major design concept was the high bandwidth we were working with. There was special consideration when selecting the high bandwidth instrument amplifiers we would be using, as well as improving our PCB layout in order to increase the bandwidth of the circuit. Our electrode coupling was also crucial. To ensure the electrodes would stay flush against the phantom head, we implemented a housing and clip for the electrodes. Finally, we had to keep in mind any material interactions that might occur, specifically with the ultrasonic gel and head cap material. This section shows all the deliverables that will be provided to the sponsor. This list includes the physical hardware such as the head cap and electrodes, the software, and any equipment borrowed from the sponsor that will be returned, as well as all necessary associated documentation such as the technical data package and operating manual.
Due to several issues that came up in the last few months of our project, we had to readjust parts of our design so we would be able to deliver on requirements given. Our electrodes had the bandwidth needed, however, they failed to improve SNR and introduced broadband noise at the low input amplitudes. Our solution was to bypass the active electrode circuitry and feed the signal directly through. The head cap, as designed and fabricated, helps give adequate contact for the electrodes to the head while simultaneously providing access to the skull for ultrasonic probes. The software component gives the visuals needed to graph the incoming data from an arbitrary source. Although C# is not as fast as C++ for digital signal processing purposes, C# provided an excellent program to achieve the visuals that were crucial to the program. Due to restrictions of COVID-19, we are not able to fully demonstrate our system. However, here are several visual aids which show the final product as it will be delivered. As seen here, the full electrode and head cap system fits snugly and cleanly onto the phantom head model. The active electrode on the left demonstrates the compactness of the preamplifier circuit. Although the deliverables this time will be a modified circuit that bypasses the active circuitry, the sponsor will be able to use the design for the active electrodes to perhaps further improve signal noise levels. Here, the software GUI is a complete user interface with controls and visual output for the user. Our team faced many hiccups and various challenges along the process of designing and implementation, including issues from the COVID-19 pandemic as well as other issues. For example, after we received, assembled, and started testing our first version of the electrodes, we found that our electrodes had much lower bandwidth than what was required. The bandwidth required for this type of amplifiers is very high for the amplifier needed. After discussing with our sponsor, we were able to find a different amplifier that, while it had a lower gain, it would give us the bandwidth needed. We quickly redesigned the electrode PCBs and tested the new active circuit components, which resulted in electrodes that satisfied the bandwidth requirements. From this and other challenges faced, our team learned several valuable lessons in the engineering process. First is to prototype early and to iterate over several prototypes rapidly. This could have helped us converge on a final design earlier. As well, we learned that regular communication is key for effective work. At times, our lack of communication with our sponsor caused unnecessary holdups. When we did have effective communication, we found it easier to develop a path forward when issues arose. Last, we found the importance of having a contingency plan for high-risk aspects of the project. As we started developing contingency plans for high-risk aspects of the design, we were able to find an acceptable design that saved time overall, rather than trying to troubleshoot and make one specific design work.